this result leads to the next question, and that is how to do processing in the inferred parametric domain. So our idea here would be to combine this inferred geometry with the natural dynamics of the time series. So the idea would be to define a likelihood function and a prior function based on the inferred geometry, and then combine the two using the Bayesian approach. So let me try to explain. Given a new measurement, what we know based on what I've just showed is how to embed it, how to translate it into an approximate state of the system in the parametric domain. Now, given that we know what is the ground truth, what is the true state of the system, we can say that it is more likely to see a measurement such that it is translated closer to the ground truth. So we model that using the local Gaussian. For the prior, we are given the previous state. What we do is we look for states from the past that are similar to that previous state. Now here we take advantage of the fact that the parametric domain is low dimensional, which means that the search for similar states from the past is more accurate and more efficient. Now, since those states are from the past, we know their future, so we can use those futures in order to define a prior. And again, we model that using a local function. Now we have a definition of a likelihood and a prior, but we don't have an analytic form of them. We just have a pointwise form, so we want to combine them using the Monte Carlo approach. The idea is to represent the posterior PDF by a set of random samples or particles, so eventually you can write the posterior PDF as a finite sum, and all we need is to find the correct weights. Now, I'm not getting into details, but it can be shown that those weights can be represented by a multiplication of the prior and the likelihood, but only on those specific sample points. So all we need is a representation of the prior and likelihood in a pointwise manner and not in an analytic form. Now, once we have an estimate of the posterior PDF, we can actually do filtering. We can define, for example, the MMC estimator, and we can track the state of the system using that framework. So I want to show another application, and that is going to be an application to biomedical imaging. Consider a two-dimensional shape that is measured by a one-dimensional linear array. So let's say we have a rigid biological material that naturally vibrates over time. We emit radiation over that specimen, and we measure the amount of radiation that traveled through the object in our sensors. And the goal here would be to track the movement, the random movement of the object in order to align the measurements. So we simulated such a model. We simulated a diffusion process that mimics the natural movement of the object, and we simulated 15 sensors that measured the amount of radiation that traveled through the object, the instantaneous amount of radiation that traveled through the object, plus Gaussian noise, and we tried to track the object. Now, what I want to emphasize here is, again, all we had is the measurement. We didn't use the model knowledge. So, based on the measurements, we had to infer or identify that the only degree of freedom in that experiment is the rigid movement of that object. And this is the result that we get. What we see here is the position of the object as a function of time. The yellow curve is the ground truth of the position of the object. The vertical gray strips are the posterior PDF estimate that we get using the Bayesian framework, and the black curve is the MMC estimator based on the posterior estimate. Now, as you can see here, I don't give, since it's just a simulation, I don't give numbers, but as you can see here, we get quite a nice tracking of the random position. And again, the idea here is that we didn't know, or the system didn't know what we need to do. The fact that the position is the main degree of freedom of that experiment was everything was done empirically, and we didn't give the simulated model to the system. To conclude, so I mainly wanted to present the notion of empirical intrinsic modeling. Here we use empirical geometry of local distributions. Then we use a nonlinear processing framework in this inferred low-dimensional, say, parametric domain. And our hope is that it can be very useful in many applications that I've just shown, especially in nonlinear problems without existing definitive models. So if we have a problem that we don't really know the model and we don't have a good guess, then this thing can